Good. Hello and welcome everybody to the last of the 3 lectures that I will give in this course. And last time we talked about shielding for control problems, how we can construct the shield to detect if an action is safe or unsafe, and how can we find alternative actions if an action that has been chosen by the agent is unsafe, how can we find a safe action instead? And today I want to bring shielding even further by talking about the topic correcting learned robot policies with human feedback. So how can we use additional information that the human can provide, that can be a user of the system or an expert doing training, to modify the policy so it can either learn more quickly or that we have certain properties achieved for the policy that requires human input. So when we learn a policy, does this learned policy really do what we want? So usually when we train a policy, you've seen that so far, we train it in a simulation environment. And when we deploy that policy into the real environment, so the deployment environment, this deployment environment usually differs from the simulation. It can be slight changes or even large changes, which is often called in literature the sim to real gap. So we can train a policy, for instance, for this vacuum robot cleaner, it needs to go to its charging station. So we have the goal of the robot to go to the charging station. We take another color. And we learn a policy. This trained policy could be, in this case, trained given the reward function we want to be there as quick as possible. So you have some greedy policy, so the robot navigates very quickly and very close to humans in the environment just to get to its charging station. However, we could also say we want the policy to be more safe. So the designer of the system could have said, I want to give more punishment when a robot gets close to the humans. And what you obtain then is a policy that is more conservative. It takes more distance to the humans before it goes to its charging location. However, it could be that this trained policy is not perceived well by users of the system. So if you buy this robot in the deployment environment, it could be that the greedy policy for you feels unsafe, whereas the overly conservative one really feels overly conservative and you think the robot is not making progress at all. So we would like to have something that is in between so that the user of the system perceives the policy as safe. So that's one of the things we will talk about today, that training a policy given our reward structure might solve the task, the goal, but certain properties that are hard to model, for instance, in this case, is it perceived as safe by humans, is difficult to obtain. And the last thing we will also talk about today is, especially for these deployment environments, it could be that we trained the robot in an environment there was no carpet, and suddenly in this deployment environment there is a carpet, and we've never trained the robot what a carpet is, how to move on carpet, and the robot, every time it goes onto the carpet, it gets stuck and cannot leave the carpet. So how can we correct this already deployed policy afterwards using shielding so that the robot learns I should not go onto a carpet, and we repair the policy even though it has been deployed already. And for that, I want to talk today about how can we leverage human feedback, either during training or after training, to correct the policies for given properties, for instance, the perceived safety, or that it can achieve its task without having to fail, for instance, when there's suddenly a change in the environment. By the end of this the session, I hope you will be able to first explain and define human-in-the-loop reinforcement learning, what it is, why we need it, that you understand how to leverage human feedback in reinforcement learning, what human feedback is in general, how we can get it into a reinforcement learning system, that you're able to explain basic algorithms and ideas for human-in-the-loop reinforcement learning, that you understand the challenges of using human feedback. It's not always easy to use human feedback, especially if it's uncertain. Then that you're able to formulate human-in-the-loop setups for different reinforcement learning applications, and how to apply shielding that we've learned so far with human feedback to various problems, so that we have a way to give verifiable but also interpretable, acceptable actions of a reinforcement learning system. And lastly, I hope that you will be able to analyze and evaluate how you can leverage human feedback in your reinforcement learning applications. As a disclaimer in the beginning, there's a lot on human in the loop learning. You can look at this journal here, where it very nicely summarizes a lot of things for reinforcement learning, given humans and social robotics and so on. There's learning from demonstrations, interactive reinforcement learning, preference learning, just to name a few. And these are very important as well, but I would refer you to that journal instead. Today, we will focus on correcting policies before and after training using the techniques of shielding and specification, what we have learned in the last 2 lectures, plus the lectures of Alexei. So I will specifically talk about these 2 papers that you can see here below. One by Daniel, PhD student at RPL here, and the other one by Sander van Waven, also PhD student here at RPL and human-robot interaction. As a small recap again, what shielding is, if you remember, the robot is interacting with its environment by getting information, and the robot is applying actions to the environment. We learned that these actions, especially during the exploration phase, might not be desired or lead to undesired outcomes because the robot is just exploring. So it could be that actions lead to undesired outcomes, and we saw that we can use shielding as a technique to constrain the learning. In this case, if the robot chooses an action, the shield is checking, does the action lead to undesired outcome or undesired outcome? If it leads to desired outcome, you can execute it in the environment. If it leads to undesired outcome, we change the action to an allowed action so that the robot only executes desired actions with desired outcome. And today we will not just talk about control and classical techniques to construct shields, but rather to bring it further by integrating a human into the loop. The basic idea why we want to do that is humans can provide additional knowledge that is hard to either encode by a designer, or a designer has just forgotten it, or it's a preference, especially for perceived safety. What I perceive as safe might be perceived as unsafe by you. So we need some kind of form and feedback from a human, a user of the system, or some other people that want to leverage the system to bring it into the learning. So the idea is that the robot every now and then, and we'll talk about what every now and then means, queries a human for feedback on its policy. So the robot just generates a lot of examples from the current learned policy and shows it to a human. This human then provides feedback to the robot, and we use that feedback to adjust the constraints and to synthesize new shields that adhere to their constraints so that the robot in the next learning iteration, when we retrain or continuously learn the policy, adheres to the new constraints that the human has given the robot. Very important for the whole lecture today is, or in general, when you want to leverage humans, humans are a very, very expensive resource and also oftentimes uncertain. So what we want to do when we leverage humans in the loop for reinforcement learning is we want to minimize the number of queries. We don't want to query them at every episode. Imagine you have a very complex reinforcement learning system with 10 million episodes. We don't want to query a human 10 million times. We want to have expressive queries so that we can actually give a human enough information that the human can give meaningful feedback. And we want that the feedback is expressive enough so that we can turn it into constraints for the robot, in this case, shields. The general idea for perceived safety that I want to talk about is today that we extend shields by not being static, but they are parameterizable. So instead of having a shield that sorts out certain actions, we can parameterize it given the parameter, in this case, theta. And theta could correspond in a shield that keeps certain distance to obstacles as the minimum distance the robot needs to keep to a human. It could correspond to the maximum velocity that the robot is able to exhibit, or the acceleration, and so on. So we can use this parameter to tune the shield given the property we want, or for being more conservative, less conservative. And what we then do is we extend our classical reinforcement learning framework that we've known so far, and I call it here the inner loop, where the environment provides a state and reward to the agent. The shield is just giving the safe actions to the agent, and the agent then executes safe actions only in the environment. We extend it with an outer loop where there's a human. So every now and then, and we will talk about what every now and then means a bit later, the robot shows the trained policy to a human given examples. Let's say we train with the current set of shields that the robot has, the policy until it converges, so the rewards are not changing anymore. We have a very stable policy, and we take that policy and using some kind of Monte Carlo simulation or other kind of simulations where we generate samples, we create n rollouts of the policy. And these n rollouts are examples that we want to show to the human that are expressive enough that the human can understand different properties between the rollout. That could be the distance to humans in the environment, it could be the velocity, and it heavily depends on the application. But given these examples, the user gives us feedback so that we can update the parameter of the shield. So this user can give us feedback so that we can update a shield parameter distribution. So in the shield parameter distribution is giving out theta. And with this new theta that we get from the feedback, we can synthesize new shields. And we do that until the human does not want to change the parameter anymore. The core idea that is behind all that is we have multiple humans likely that are giving us feedback. And because the human feedback is also uncertain, instead of saying that the human gives us an explicit representation of what theta needs to be, we model it via distribution. So theta becomes a random variable, and this random variable is what we want to get a measure of, given a lot of samples that the human provides. So we want to infer the right distribution of theta given multiple rounds of human feedback. So let's talk about a bit more how these shield parameter distributions work. So what usually I would recommend for these kind of cases is you model the shield parameter with one distribution. So you have one distribution that models your theta, and we have one distribution that models the human parameter guess, and this one is called FH. Why is that the case? If you want to synthesize new shields, and you synthesize it directly from the human feedback, it could be that the human feedback is switching because it's very uncertain feedback suddenly, and then you have high and large parameter jumps, which we don't want to achieve. So for instance, if we give, a human gives feedback samples in the forms of, let's say, textual feedback from this was very unsafe to it was a fine policy to very safe. It could be that in one rollout examples that we show to a human, that the humans all say, oh, it was very safe. And then we think the parameter was good, but the next time they say it's very unsafe because of the randomly created examples. And with that very unsafe feedback that we get, the distribution would suddenly change so much that our parameter is jumping. So we would get one very conservative shield, suddenly a very greedy shield, again a conservative shield, and this alternating we don't want to do. So when we have two distributions, it corresponds to some kind of smoothing process. And the advantage is higher robustness against uncertain feedback. So just to recap, we have one distribution that models the human. So the human gives us feedback, we update that distribution, and with this distribution, we update the real shield parameter distribution. And because we have one distribution in between, it is not jumping so much when we have uncertain feedback. You will see that in some slides. So the general chain is we have one shield parameter distribution where we first sample one theta or multiple ones that we train our policy on, and then show the humans and examples given the current shield parameter. And the humans give us feedback on how they perceive the policy to be. For instance, if we want to check safety, they could give us feedback in the terms of very safe, to being fine as the middle ground to very safe. With these feedback samples, we first update the human distribution. The human distribution, we can just simply map the data that we have, if it's textual data, because it needs to be interpreted by the humans, into a machine interpretable way. So we can use a mapping function that says, okay, given our very unsafe to find to very safe labels, we model it as when it's fine, it's the center of our distribution, it's our mean, and everything else is in steps to the left and to the right of the mean. With all the data that we have, we can just impose a Gaussian over that. So we can update this distribution of the human with a new mean mu and a new variance sigma by just using classical probabilistic theory by saying we use all the mappings, sum it up and divide it by the number of samples we have. So we get the new mean of our distribution. And the same for the variance, we can do the same, and we obtain a new distribution for the human given all the samples that we obtained from the human. The nice way of these kind of things is you cannot ask humans in general, what do you think of that value? Should it theta be 1.1 or 1.0 or 2.6? You need to have some kind of interpretable way. And a lot of people in human-robot interaction, they use interpretable scales, let's say either a Likert scale, where you could say from a scale from 0 to 7 in discrete steps, 0 being unsafe, 7 being very safe, what do you think, how would you rate it? Or that you have some textual form like here, very safe to find to very safe. We got a question. So the question was, how do we determine the convergence of theta in human feedback shield synthesis? Very good question. In the next slide, we will talk about that. So first here in this slide, we just update the human distribution. And here you can also see the argument I gave you in the last slide, why we have two distributions. If we compute the feedback all the time, the distribution like that, if the samples changes a lot, so let's say the humans always say very safe for that example, and for the next one, very unsafe, the mean will change dramatically. Whereas if we use the second distribution here, and the real parameter distribution, we can update the shield distribution through Bayesian inference. So the idea is that we take the newly updated human distribution, FH, and we update our shield distribution by generating samples from the human distributions and use the samples to compute the posterior. So the likelihood, what is the true parameter that the humans actually want? So we get a set of G of samples from this human distribution and the likelihood of the two parameter distribution. So what is the true mean and variance given our set of samples? We can compute that using the likelihood. The cool thing is, we can do the Bayesian update of this shield parameter distribution just by using the posterior computation formula given here below. So basically, given all the likelihood of our samples and previously what's the likelihood of certain parameters, we can update the new mean and new sigma of our shield parameter distribution. For Gaussians, which I would assume is most of the time very useful for you because human feedback is often in Gaussian distributions or in multivariate Gaussian distributions and so on. There are closed form solutions for computing this posterior, where you can obtain the variance as this fraction as well as the mean. Here it's important, n corresponds to the number of samples that we use from the distribution that we sample, and x bar is the mean of all the samples. And you see the most important parameter in this closed form solution is the number of samples in G. And that's very important. It's one of the hyperparameters that you need to tune. The more samples you take from the human distribution, the more you can change the posterior, or the more information you have for the posterior. The less samples you take from your human distribution, the less information you have also for computing the posterior. And then going back to the question we had, when do we stop? So we have now two distributions. One where the human says that's what we think, and then another distribution where we sample from the human distribution to update the posterior. If those distributions are very close to each other, then we can say the human is agreeing with what we have so far as the true estimate of our parameter. And we have learned so far in other lectures, very nice for that is the KL divergence. So if we compute the KL divergence between these two parameter distributions, so the human as well as the true estimate of the shear parameter, if it's sufficiently small, we can say we converge to a consensus where the human does not want to change our parameter anymore. So if the KL between our FF and of our FH is smaller than a given epsilon that we want, we can agree and say that we come to a consensus. The human does not want to change anymore. Here on the right side, you can see how this prior posterior would look like. So in the beginning, we have a prior in blue, and we might sample 4 parameters theta that could be a guess, and we train 4 different policies, show it to humans, how they perceive each of these policies, and we get feedback given all these thetas. We update the human distribution first, sample from this human distribution, and compute the posterior. You can see that we narrowed down with the initial guess already where the parameter is. So we can see in this regard from the picture, the humans mostly liked theta 3 in this case. That is very close. And then what we do in the next step, we sample from this new posterior, new shield parameters that we use for the new shields, train again, do it until the KL divergence is sufficiently small.
Question.
Yes.
So we only use human distribution for sampling this G, right?
Yes.
Okay.
Exactly. Thanks. There's another question in the chat. So how do we update the posterior where we do not have the true parameter distribution in the last slide? So the posterior is updated given the sample. So we don't know yet what our distribution is. When you start the framework, you need to have an initial guess. You could say, I initialize it with a very possible likely mean and standard deviation. You need to have a large standard deviation so that you can actually get some change. Because as you say, that's very good and a very important point. When we update the posterior, our old mean and variance is part of it. If the variance is very small already, we are very certain the posterior update is taking longer. So we want to have a very uncertain prior in this case. That's why we have in this slide the prior very wide. We use the samples to update the posterior, just given the samples, and we do that as long as we can do, such that both distributions do not change anymore. The KL divergence is sufficiently small. So it's a very good point. Initially, you need to set for the first prior, what is your mean guess, as well as the variance guess, and then you can update. I hope that answers your question. Thank you. I want to go to.
Can yes, I ask please? One more question?
You can ask as many as you like.
Why do we sample and then use it for likelihood? Why can't we directly find likelihood with the probability? Because we know the parameters of the human distribution, and we know the probability distribution of the shielding. Why can't we find the likelihood directly? Why are we sampling and then finding the likelihood?
Yeah, that's a good point. So for that case, if we have uncertain feedback, we will get a not clear distribution. So in order to have a slower convergence, so that the posterior is not drastically changing, we use the samples to update and to compute the posterior. If you would directly compute it, you have also larger changes again. And by saying we take samples from it, we can control as a hyperparameter how slow we are changing the posterior so that we don't get these jumps. Because the smoother it is, the better it is for these kind of frameworks. So all the time you have strong parameter changes in the shields. You're alternating between this was too good, this was too bad, this was too good, this was too bad. So it's similar to what we showed you for control, that you want to go to a reference value, you oversteer, you're crossing the reference value, then you try to steer to the other direction, you oversteer again, and you're just alternating around your optimum. And with these kind of samples, then as a parameter, you can control how much information you want to take from the human distribution to update your onto computer posterior. Hope that answers your question.
Thank you.
Thank you. Let's take an example where you can see everything in action. So we created an example based on lunar landing, where the task is for the small Luna that you can see here to land in the goal region. This Luna has a main engine pointing downwards, and it has two engines as helper, a right engine, a left engine. And we created an artificial benchmark as the safety is not overusing the main engine. A human would say that is usage over 85%. Could be any other number. It's just to create some human knowledge that is we try to simulate as being hard to encode. And the shield limits the main engine usage. So theta is in the range from 0 to 1. 1 is 100% usage of the engine, and because you can also brake with an engine, you have minus theta to theta. So if we change theta to a larger value, the agent can use more of the main engine. Whereas if we choose a smaller theta, the agent is only able to use larger percentage of the main engine. And in this case, to analyze the property, we simulated the human feedback by generating 10 humans that give us correct feedback. But we'll also look at this later. What happens if certain percentage of the humans is giving you random feedback, as real humans would do? So first, let's look at how this framework that I explained to you would look like for this case. So on the left, you can see the rewards that we have for the shield synthesis, for no shield, and for optimal shield. So you see optimal shield would directly train with the perfect theta, which in this case is 0.7. And blue is how it would behave over training over time. And they're pretty close, they get the average award. Whereas the no shield version takes much, much longer to converge because we are not leveraging the additional knowledge that the human could give. In the center, you can see over as the x-axis, the episodes, how the shield mean from our shield distribution changes. So you can see from we allow the main engine to use everything. So it's the very conservative initial prior that we were talking about. We allow everything. This shield parameter updates with the human feedback until it converges at around, 70 episodes to the final value of 0.7. And there the KL divergence stops because we are sufficiently small. So we arrived at the parameter for the shield that gives us the best performance in this case. And on the right side, you can also see the number of successes of landing also corresponds to that case. So we can use the knowledge that the human could have of, this is how I would steer a system, this is how it feels like, to give additional knowledge. We also try to train the no shield version for much longer. You can learn the task, but you need much, 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 much more episodes. Whereas the shield synthesis and the optimal shield are very close. So what we learned from that is also that if we update the parameter online, we don't lose a lot of performance because we are very close to the optimal if we would directly start with the best parameter. So what we learned from that is it makes sense to leverage additional human knowledge and to update the shield parameter distribution over time is not losing so much. But how does it look like if we have non-perfect input? In this experiment, we increased the uncertainty in the human feedback. So remember, we had 10 humans, and we increase the uncertainty in the human feedback by saying 10%. So one person is giving random feedback, saying, oh, the parameter needs to be higher or smaller, or it's fine. 30% and 50%, so 3 or 5 humans. And you can see on the right side the KL divergence over time. We first see we can still converge even though we are up to 50% of random feedback, because still 50% is all the time saying the right answer or giving good estimates, but we just need much more time to update the distributions. And we can also see that if we have higher uncertainty, it requires more convergence. So we need more episodes in this case. So I think, what is it here, around 70 if we have perfect feedback all the time. Whereas if we have 50% randomness, it converges at around, 180 episodes. So around double to triple given from 0 to 50% of randomness. So that's very important to consider as well, that human feedback is nice if you use it in your reinforcement learning system, but you need to have a way in order to analyze how can we represent the uncertainty. In this case, we make use of modeling the parameter as a distribution and looking at how much are the human and our true estimate, so the posterior, equal to each other by using the KL divergence. And the KL divergence is giving us a nice measure of how close the human guess and our guess are in reality. And if it's very small, which you see here in the plot, then we can argue that we converge to a consensus.
Sorry, may I ask two questions? First,
yes.
What is this optimal shielding? Is this the last parameter that is converged to that? Is that
exactly one? The 0.7 that I showed you in the previous slide is the optimal one.
But if that's the case, let's say in 5,000 episodes, they actually should overlap basically. After 5,000,
you mean here in the right picture?
Yeah, number of successes should be exactly the same.
It's cumulative, the number of successes, because yes, perfect. Okay. So that's why we have less in the end.
Yeah, perfect. And about the randomness, so how do you introduce that?
So we have 10 humans simulated that in the beginning now 0.7 is the right value. So every time they see a rollout, they compare it to the true value of 0.7 and say it needs to be higher or lower, given what we tested in the policy. And when we introduce randomness, we flip a coin. We say, if you give me the value, we say, oh, now it needs to be higher, now it needs to be lower. So we just say anything all the time for 50% in this case of the humans. And that's also a good question. If you have such a system, test your system. If you're able to simulate feedback, you can also take an experiment where you got your feedback and just randomly flip the feedback that you got, just to see how robust is your framework against these kind of uncertain feedback. Very good questions. Thank you all. Before the break, the last thing I want to show you today for that perceived safety part is an example where we simulated or trained an agent that is tasked for social navigation. So this social robot here, Peppa, is tasked to get to the goals, which you see here as these small stars, while not bumping into humans, and the shield constrains the minimum distance to humans. And the parameter theta defines this minimum distance. So we want to achieve a shield that is perceived as safe. And perceived safety means, in this case, the human keeps a preferred minimum distance to obstacles around. By using the framework, we can start from a very unsafe framework, unsafe policy, a shield, to one that in the end converged perceived as safe. And if you remember previously the slide where I showed you the prior posterior, these are actually the prior posterior for this kind of, for this setup here. So in the beginning, this robot policy was perceived as unsafe because it's keeping very low distance to the humans. You see here, was very close to it. However, if we run multiple rounds of our framework and update the parameter until it converges, we get a policy where the robot is keeping more distance to humans, which you can see here. It waits until there's enough space to pass to go to the goal. And this has been done not by doing reward engineering and so on, but just saying we have a formal shield that we parameterize with a simple parameter, what's the minimum distance, and updating this minimum distance by taking these kind of videos of the policy rollouts, showing them to humans. In this case, you could use, for instance, Amazon mTurk, where you deploy it to online people that see these videos. It's enough information from the video, so it's a meaningful query. And you could say, what do you prefer? The left video, the right video? Or you can say, is it very unsafe, very safe, fine. And with the feedback you get, you just update your theta until it converges, as I've showed you before with the KL divergence. Before we go to the second part of the lecture, are there any questions to perceived safety? So far what we've shown is you can parameterize shields, and the focus was on how can we use human feedback to update the parameters. Just the parameters. Just to recap, because sometimes also for me, what I talked about so far was how can we use human feedback to parameterize shields to achieve certain properties. And I went back to the slide that I showed you in the beginning, this overall idea, how we can use humans to provide additional knowledge. So we saw already that humans can provide additional knowledge by changing parameters of the shield. But here in the slide, you can see we are basically adjusting or saying synthesized shields. Previously, we synthesize new parameters of the shields. Now it's about how can we use humans to actually create shields that have not been created by a designer before, so that we can correct robot policies. And here I want to talk about some kind of different things instead of perceived safety, but about policies that fail. So when we deploy policies in a real environment, they may fail due to environmental changes. So for instance, this cooking robot, which you can see here on the left, there could be that it fails because it needs to fetch a tomato slice, but there is no tomato slice, there's only a full tomato. So there are certain missing items. Or you have some undesired outcome, which I explained to you in the beginning, when we have a robot that suddenly experiences a carpet that was not there in the simulation environment and it gets stuck on the carpet. How can we use human feedback in order to correct the policies even after they have been deployed to a real system? And in this way, I want to talk about how we can use that human feedback to create shields that adjust the policy so that we avoid the failures. So the idea here is that the robot queries for help when it encounters a failure. So we have the agent and encountered a failure. It queries for help for non-expert. Non-expert in this case is to emphasize that these humans are not necessarily roboticists, reinforcement learning experts, and so on. So it could be the homeowner, the robot owner. It could be also someone who has just experience in the task that the robot needs to do. This non-expert provides feedback to correct the failure, telling the agent you can avoid the failure, for instance, with the carpet by not stepping onto carpets. And then we use our shielding concept to create a shield that blocks all the actions that would lead to the failure of the robot. And with that shield, the agent can avoid the failure in the future because it blocks actions that lead to a failure or adjusts the actions so that there is no failure. This basic idea I want to elaborate a bit more in the second half of the lecture today. And here I want to focus on high-level decision-making tasks first. Why? High-level actions are interpretable by humans, because if we take care of a control problem where it's about trajectories, about states, and so on, continuous, it's very difficult to interpret that for humans. However, if you have high-level decisions, it's more easy that a human can say, if the robot has actions such as pick, place, move, and drop items, which you see here, that the human can suggest high-level actions to correct failures. Moreover, it would be nice if it's a common daily task so that these non-experts give you feedback so that the robot can correct its policy. Because if it's something that you need a reinforcement learning expert for, let's say the robot has a failure because there's some faulty LiDAR in there, it's very difficult for a homeowner to use it. So we focus on high-level decision-making tasks where humans can get interpretable actions and states, and these non-experts can provide feedback based on that. First, in this framework, the robot, when it encounters a failure, it needs to send a query to the human. Similar to before, when we talked about the parameter update, the robot needs to send meaningful queries so that a non-expert in this case gets what's the state of the agent, what's the action that failed to, and how or is there enough information to provide feedback in order to correct the failure? So in this case, it's the classical failure trace and environment overview. Could look like that. If you have the same kitchen environment, the robot could show I was here. I was executing the following actions until the failure. First, for making a sandwich, wanted to fetch a sliced bread, then getting some ketchup, then salad slice, and then wanted some chopped onions. But there is only a full onion, but not a chopped onion. So it's unexpected. And the robot could give humans feedback that's interpretable, like you see here on the right. I failed to complete my task. I tried to fetch a chopped onion, but failed. What could I do to avoid this failure and complete the task in the future? This kind of information you can show to a non-expert so that the non-expert understands what's the robot's state, what did the robot want to do, and how can we get feedback on that. The general idea here is in 3 parts. On the left, you see the classical reinforcement learning system that we talked about. That's A, where a reinforcement learning agent is training in a training environment given some shielded actions. We deploy this policy, and if the robot encounters a failure, it queries a human, and the human gives feedback. For instance, if there's no chopped onion, fetch an onion and chop it, because I saw you have an onion, chop it. Do it new, because someone maybe did not chop the onion before, so you can correct it. So we talk about very high level and examples so that it's easy for us also to get the concept. Fetch the onion and chop it. We can take this natural language to put it in an NLP framework that gives us what are the actions and the action sequence. And we take this feedback that we get to correct shields. And today I want to talk about 3 kinds of shields that we can introduce. That's the action refinement shield, where we say action A1 led to a failure. You need to do another action A2 before executing A1. Where there are certain items missing or certain parameters of the action fail because you want to grab that drawer, but the drawer is locked and you need to open another drawer. Or certain actions are forbidden, that's the 3rd one. And you need to cancel out certain actions that lead to undesired outcomes. When we generate the shield based on the feedback, we can retrain by bootstrapping our previous policy. So in case some changes in the optimality of the policy, but you could also deploy a shield in most of the cases, depending on the system already directly, but you might get suboptimal results. The first shield that we talk about today is action refinement. And we first introduced the state transition function delta, which takes in the state at the current time t, and the action the agent wants to execute, and we obtain the next subsequent state as t+1. We have a set of desired states as desired. That is the set of states the agent can have without the failure state that it encountered. So we know it needs to remain in that state so that we don't have a failure. In action refinement, we take what the human suggested and encode it into an alternative action sequence, which is given by this function C. So for instance, if there's no chopped onion, the human suggests fetch an onion, chop the onion, and then you can fetch chopped onion. The feedback function C gives for the current state and the action that the agent wanted to execute a small trajectory of actions that the human suggested instead. So you see when we look at the shield, refine action, if the action A results in a state when applied so that we are in a desired set of states, we just execute it. It's the same thing that I showed you before in the last lecture with the invariant sets. We keep it. If, however, we are leading to a state where some undesired states, in this case, oh, you want to fetch the onion, but there is no chopped onion, then we execute the feedback that the humans give instead. Here you can also again see why it's important that we check the sanity of the feedback, because if there's one human and it just suggests wrong feedback, we just execute something wrong. So we might query multiple humans and also do some consensus. We get 10 times 10 feedback and 8 of them give the same. It's more likely that those 8 are right than the other 2, of course, depending on the difficulty of the task. The second shield is alternative item. So here we talk about that an action A has some parameter P, an object, for instance, that the action manipulates. It could be open a drawer, and P says which drawer. It could be chop an item, which item. P is the item that you need to chop, and so on. And it could be that the original item, PO, original, is not available, but instead we have some alternatives. So you can, for instance, imagine you have a robot that needs to bake a cake, and you need a certain wheat flour, but you don't have the wheat flour anymore, but you have a different kind of flour, let's say almond flour. A human, as we do it, we directly know there's an alternative. We just use the alternative and we can still succeed. An agent does not know it. The same when you need to open a drawer or something else, the robot might not know it because it hasn't learned it in its simulation. We can then suggest as a human an alternative. So then an expert suggests this alternative item PA, and the shield, alternative item in this case, takes the action A that the robot wants to execute with the original item and says, okay, you can execute it if this original item is in the environment. However, if the one is not in the environment, we execute the suggested alternative instead. So basically, we are injecting the knowledge of the human into the action parameter. The last shield is very, very close to what we've talked about already in the lecture of control, but here to decision-making task. So we have certain actions that may not be desired anymore in the deployment environment because of these changes. Let's say with the carpet. Suddenly, when we go onto a carpet, we get stuck. We can use the feedback from the human to label forbidden actions, say like, oh, if you're going on the carpet, you will get stuck, so don't go into a carpet. With that feedback, we can label what kind of states, in this case, being on the carpet, is undesired, and we can automatically check and create again this desired set of states, and we can check which actions lead to these undesired behaviors. If those lead to undesired behaviors, we just don't use that, and instead obtain a set A allowed, which is a subset or equal to all the possible actions that the robot can execute. So we are basically reducing the number of actions that the robot can execute, the agent, in the state S, given that the action always leads to a desired outcome. So for instance, again, with the carpet example, if we're going onto a carpet with the action, it's not desired, we don't execute that, but instead the agent has the choice to take other actions that, for instance, go around. Here's an example where you see how these three shields work for this kitchen environment that I showed you in the beginning. It's a nice human-robot interaction environment that is used for reinforcement learning. It's the overcooked AI-based environment. And the task here for the robot is to prepare and deliver certain dishes. And it's interpretable because it's a common daily task for all of us. All of us know how to chop items, what it is in the salad, what you need for a sandwich, and so on. It's a grid environment, so it's also discretized states. The agent has certain facing directions and so on, which you can see here with the numbers. So 0, 1, 2, 3 until 7 are the facing directions, and it has actions such as turn clockwise, turn counterclockwise, fetch an item, drop an item, and deliver an item to the delivery. We could now task the agent to make a salad. So for instance, we could simulate that in the training environment, there was always one person that delivered tomato slices in the morning, but suddenly in the deployment environment, these tomato slices that were in the environment are not there anymore. So we have a failure. The agent says, I tried to fetch chopped tomatoes, but they're not available anymore. What can I do? The non-expert in this case can suggest to, if there are no tomato slices, first fetch a tomato and then chop the tomato. And then you have new tomato slices. So basically equipping the robot with an alternative action sequence to correct the failure and learn new knowledge in this case. For that kind of task, we would create an action refinement shield. And here in the next slide, you can see the experimental results, where on the right side, you see the total reward over the episodes. First, for without shield, that's the red line. So without shield, we can also relearn. So the agent with a lot of random exploration at some point learned, oh, if I'm fetching a tomato and chopping it, suddenly I have tomato slices again, but it needs more time than the shielded version, where humans said, this is what they need to do, take it. So we converge faster. And the good thing is, because shielding, as we've learned so far, is a formal technique, it always refines these actions. So it's a verifiable way so that the robot is not encountering these failures. Whereas if you train without, you need to have this kind of change in your simulator as well. And you have these kind of resets because the robot will encounter this failure still because it needs to learn more and more. With the shield, we have faster conversions. But as I said, you need to check the feedback quality. The black line in the example is a shield that is synthesized from incorrect feedback. So a wrong action sequence was suggested by humans. And you can see that we converged, but not optimal. We don't get the reward we need. It's because humans suggested something that might need to lead to an infinite loop or to just a bad action sequence. And this is very important for everything when you consider humans in the loop for reinforcement learning. It is an uncertain source of feedback, and you need to treat it like that. So in this case, you can see if you get incorrect feedback, you need to have some kind of sanity checks before to check if the feedback is of good quality, and then you can deploy the shield to the robot. The last example that I want to show you today is delivering the coffee with the carpet. So we have an agent that needs to take the coffee here and brings it to the delivery. And the failure in this case in the environment is that the robot gets stuck on a carpet that was not in the simulation environment, but this case in the deployment environment. And the failure is that the robot gets stuck on the carpet. So what the non-expert could suggest is similar to your vacuum cleaner. And it's a realistic example because vacuum cleaners, they get stuck under over carpets, they get stuck over certain carpets or under tables and so on. You can suggest to your robot to never move to these carpets then. In this case, the framework could synthesize automatically a forbidden action shield, where the human feedback is used to say, oh, every time the robot is on a carpet, we don't execute the action that leads me to the carpet. Here you can see, again, the learned rewards. Let's first look at the shielded one in blue. The shielded one learns it. We are converging. It learns it perfectly. In this case, after 24 episodes. The without the shield in red never learns it because it does not know when I'm on the carpet why it happened. So there is no reward, a negative reward, why you are on the carpet. Just boom, you crash and the episode finishes because you're stuck. So by using some reward engineering, that's the penalty one in gray, giving penalties whenever you are on the carpet. So you need to encode it and go back to your reward function. The robot can learn, but again, the convergence is much later than the shielded version. And what we can also see is, again, for incorrect feedback, in this case, the incorrect feedback is correct for that environment. It's learning the task and it's converging quicker than the correct feedback. But, and this is also very important, incorrect feedback might result in non-generalizable solutions. What do I mean with that? In that environment that you see here, if the agent is here where the A is, I could say, never move on carpets, which is general. Or I can say, in this case, move down, move right, move up, and you're at the delivery. This only works when the carpet is always there in that environment. So that's another kind of way where you see that the feedback you obtain might work training-wise, but it might not be general enough. So we learned that feedback needs to be checked for validity, for quality, but also if it works, it might be leading in a non-generalizable solutions. And of course, there are a lot of literature now and also recent research that looks into how can we first do these sanity checks. And if we check that there is some incorrectness, how can we ask other humans to correct the feedback? So we get feedback on the feedback and try to correct it. It could be also lifelong, is also what Alexi, for instance, showed. When you learn specifications, how can you do continual learning and continual improvement of specifications? So this brings me to the end of the lecture for today. Today, we looked at the central research question: how can we leverage human feedback to correct policies during or after training by merging the feedback with the formal methods technique of shielding that we learned so far. So we have a way to give verifiable results, and we can change what kind of properties we look at by getting human feedback. This human feedback can provide additional knowledge that is either hard to encode or only acceptable by the user of the system. So the user needs to give us this feedback, or not the designer of the reinforcement learning. We learned that there are different ways to integrate humans into learning. I talked to you in the beginning that there is preference learning, interactive reinforcement learning, where you, for instance, take the robot manipulator and guide the trajectories and so on. But here we looked at how can we use shielding and human feedback. We first looked into how we can use parameterized shields. So a shield that has a parameter of influencing certain properties of the shield, how we can learn the perfect parameter for the users. And at the second, we learned how we can create new shields based on human feedback to create the correct policies. In general, we saw that using the shielding, we can speed up learning. We can improve acceptability, in this case, obtain robot policies that are perceived as safe. And we can also correct policies. Very important is we need to consider the number of times we query a human, the type of query. So what is the query showing? It needs to be meaningful. And the type of feedback. So the feedback needs to be meaningful as well. If you just say good or bad, might not be enough. Maybe you need to give more skills, more fine granular feedback. And as I said, we looked at how to update parameters of shield during learning, given two distributions and KL divergence, so that we have reached a consensus. And lastly, we also looked at automatic and verifiable failure correction after deployment, using shields that we create on the fly from the human feedback for refining actions, providing alternative items, or for not allowing certain actions. So this closes the whole chapter of shielding from the side that Alexi in the beginning talked about, from classical specifications from temporal logic to the continuous shielding of control, where we talked about reachability analysis and control invariance, to high-level decision-making and how we can use human input for shielding. Next week, we have another lecture by Alex talking about more applications in the applications of biology and chemistry. I hope you will also tune in on that. But other than that, thank you so much for listening today and for your questions. And I will stay again here for some minutes if you have more questions. Thank you and see you next week. Bye-bye.